a great team here with us from the University of Glasgow, and I would like to introduce Dr. Hensley, if you'd like to come up. Are you Dr. Hensley? Hudson. Okay. Well, I was just going to say Dr. Hensley could introduce you.
Hensley. Oh, Hensley. Okay.
Know more about you. Okay.
Who's Hensley?
Okay.
You're.
You don't know who's on first. So, if you'd like to introduce Dr. Hudson,
I'm just surprised. Okay.
I'd love for you to come up, and that way you can talk about the project and turn it over. Okay. All right. Thank you all for being here.
Okay, this is a surprise. Dr. Hudson, and his first name is Hugh, was born in Texas, served various positions, a distinguished career, many positions at Hawaii, University of California, Berkeley. He was at San Diego for a while. It was one of the first places I met him, way back in 19... moved to Scotland. We kind of did a reverse thing. I came from Scotland to here. And I say here, I mean the United States. I've kind of bounced around a little bit, not Odessa, my first trip to Odessa. But Dr. Hudson, Hugh, moved to Scotland, thereby acquiring the name Shaggy, which is Scottish for Hugh. So you were talking about Shaggy did this. As well as being, prolific author, anybody know what H number is? Okay. I don't want to ask around your H number. Your H number is more than 100. You're kind of a good author. And you can Google Scholar Hugh here and see what H number is. It's way up there. That means at least 100 of his articles have been cited at least 100 times each.
Wow.
Yeah. I'm lucky 3 of my autos were cited once, but so he's done research into solar physics, into gamma ray physics, and all kinds of high energy physics throughout the universe. And there's always been an eclipse aficionado. I first learned about this when I saw a poster at a meeting about 2014 or so, which alerted us to the upcoming 2017 eclipse. And this street across the United States, which passed through a list of towns, and the list of the towns on it, and one of them was Bowling Green, Kentucky, where I live. Well, it's interesting. And the idea was that we would get citizen scientists to help scientists make observations that there just weren't enough scientists to make by themselves. So by taking people along the eclipse path and synthesizing observations made by ordinary members of the public, like you or me, we could make a movie that just could not be made any other way. People have tried to chase eclipses with airplanes, where you can stay in totality for just a little bit longer. This precious few minutes of totality, you can stretch by a minute or two. If you have an airplane, you don't mind taking the picture of the eclipse through a window. But the idea of using different observers and technology to synthesize this together is this man's responsibility. About a couple of years ago, I had an opportunity to participate in the Citizen Science Project. I said, what happened to that mega movie thing, as it was called then here? And he said, we can still do that. And there's really cool science you can do with it. You'll hear about it tonight what that really cool science is. So at that point, we kind of bestowed upon Hugh the title of honorary professor at Western Kentucky University. He comes to all our Zoom meetings, even though he's 6 times on the way there, has flown all the way here from Glasgow, Scotland, to be here for this event, to present this talk, and to represent what I think is a really, really cool project. So, without further ado, Shaggy.
Thank you, George. That's great. As you can probably hear from my accent, I'm from Texas. And so it's a great pleasure for me to come back to this country, this area, which I've driven through many education before. I was a student at Rice also, so 4 years at Rice as part of my background. Okay, and so Gordon left out by Japan. I spent 10 years in Japan to do the part of history. In any case, the 2017 Eclipse was the first opportunity to do this image patching together, the mega movie, but there was also another aspect of it which didn't work very well, and And that was the aspect that we're talking about now with SunSketcher, which is to use the smartphones in a way that I'll describe in a little bit of detail. So my plan is to talk about eclipses just in general, and then I'm going to slip in a bit of, sort of educational stuff about astronomy and the sun and solar physics and things like that. And then in detail about the SunSketcher program itself, which is a very simple and wonderful app that's been built by this great group of people from Western Kentucky. So, with no further ado, my assistant, Esmeralda. Oh, okay. We'll show you what it is. What's happening tomorrow? So this is me on PowerPoint yesterday doing this. So you can go click that. You can see the annular eclipse happening. So those first 3 slides just show before, during, and after. During it's manuals, right? Just bright rain. And so this is to distinguish it from a real eclipse, which is I really encourage all of you to enjoy seeing with your own eyes. And you can do it even if you live in Odessa, where it's not going to be next year. It's going to be pretty close. So just drive down to the middle country or Austin or someplace like that, and you can see it. Okay, so the next slide I think shows what we call a second contact. And Gordon and I have been arguing about what is the actual definition of second contact. But here, it's just when the tangent point, right? There's 2 discs, they're almost discs, so they just match at one point. Not very well defined because it's a very long, thin point. That's second contact. And the next slide shows, third contact, and that's the other side of the sun, right? So I think this is just to clarify what's going to happen tomorrow. And the main thing is, next slide please, if you want to watch it, you have to do it with eclipse glasses, right? This is a requirement, otherwise your eyes will hurt. And it's bad for you. So you can also do it by projection. And I think at the Stonehenge we're going to have a colander. Is there going to be a colander? Did we buy a colander?
What?
Colander.
Yes.
We have that.
I'm
Okay,
going to go to Walmart. Yeah.
Okay, so that gives you an amazing, fantastic multiple view of tiny projected images of the eclipse happening. Okay, so I think that's the main, the general stuff. And now, next, the total eclipse is this, and this is what I encourage you to want to go and see. And you can see, actually, it's going right through Dallas and Fort Worth, all the way up through Nova Scotia and out into the lake. So this is another opportunity, I think, for this mega movie kind of multiple exposure movie of the corona to be made. And it's also an opportunity for us to do this SunSketcher physics, which is not really the corona. Our objective is to study the actual sun itself, the surface of the sun. Okay, next slide, please. Yeah, so that just illustrates in the total eclipse, the moon covers the entire sun. You can take your glasses off and just admire out there what the question marks are. The beautiful corona. I just saw a great image from the 2017 corona that was taken during it, with multiple exposures stacked to give a huge, beautiful view. Okay, so next. Right, so the question before us this evening is, what links Odessa relativity? And of course the answer is on the next slide. It is the sun. That's why we're here. So I'll explain now some of that. And so I want to, at this point, shift into educator mode and talk generally about the sun and astronomy, right? Because this is a good opportunity to explain a few things. The sun is really just a star, an ordinary star, a slowly rotating yellow dwarf star. And the interesting thing about the sun was it's a very nice thing that it's there, because otherwise we wouldn't be here. But the very interesting thing about the sun is that it's magnetized. It's got a large magnetic field, a very complicated one. And I'm going to show you a movie that shows you how that works. It has remarkable patterns of variability, this magnetic field of the sun. And one of those is the 11-year sunspot cycle, which many of you don't know about. So how many of you know about 11 years? There are a few people who have heard of this, right? So I found today that some expert people didn't have any idea about this. And so if you ask an expert, the sunspot cycle, it's 11 years. research on why is it 11 years, they won't be able to answer that question because it's one of those things that is not understood by our theory, any theoretical development. So it's just there, but it's wonderful because it means that we have periods where there are no sunspots and periods where there are lots of sunspots. And then there are flares and coronal mass ejections and things like that. So I'll show you the way the field evolves in this movie. Next slide. No, sorry, I ahead of myself. Yeah, this is, okay, so the magnetic field on the sun is sort of like that of a bar magnet, or a fridge magnet, except that it's in patches. Most of it is in patches on the surface of the sun. One patch is what we call a solar magnetic active region, and this sketch kind of shows you a cross-section of the sun, the yellow part, inside the sun. Below the top surface there are convection cells. That means it's boiling. There's a boiling kind of convective motion of the gas that's inside the sun, okay? And then the magnetic field, the lines of magnetic force pop out through that top surface, and where they cross through that surface, you get a sunspot. This is a simple picture of how it works, what we observe. And the part of the magnetic field that's above the surface is what we observe through flares and coronal mass ejections, and I'll show you movies about that as well. So I think the next movie will be blue for the north and yellow for the south. The magnetic field has got poles, the north pole and the south pole, and so they appear in the images here as blue and yellow. So play the movie. This is the sun, blue and yellow active regions. Now why is it not playing? There we go. You figured it out. Okay, so the sun rotates. The regions come and go. You can spread them out into a Cartesian projection like this, and watch that as a movie over the years. You can see the time axis there is 1980, 90, 2000. Spots disappear, and they come back. And they have this amazing pattern, blue and yellow, yellow and blue, and it's just remarkable. So the movie just stopped by itself there. That's okay. I think people saw it, but we can play it again because it's so wonderful. You see it unrolling. Now just every vertical line in this image is a summation. Okay? Minimum, maximum, minimum again, maximum. And the colors you probably didn't see, but they switch. Every 11 years, positive and negative switch, and so it's really a 22-year cycle that we call the Hale cycle, after Hale. Okay, so that's solar activity. Next slide, please. Right, so the sun itself is amazing because it emits, well, it's very close to us. This is the closest star, right? So we can see it in almost every wavelength. So from left to right, there are 3 different wavelengths here that I'm showing you. On the leftmost, it's the radio sky seen at 100 megahertz, right? This is a higher frequency than your normal, broadcast radio, but it's still a long wavelength, like 2 centimeters, something like that. So the whole sky there on the left has objects in it, and one of those objects is the sun, but it's not the brightest object. So at that wavelength, in these radio wavelengths, the brightest things actually are galaxies. And so, but the sun is there, and the sun is, of course, if you're looking in visible light, which is what our eyes see, the sun is, of course, dominant. Day and night, it's like night and day. So this is a picture in the middle, which is labeled H-alpha off-band, but it's just a picture of the sun, the sunspots. And on the right, you're seeing a picture of the sun in very high energy gamma rays. So very high energy gamma rays, the numbers up there give you the orders of magnitude of the frequency of the radiation, right? 100 megahertz is the radio band, 10 to the 15th hertz, right? 5 magnitudes, 5 orders of magnitude higher, it's visible, and then you go to 10 to the 27th hertz, which is where this image on the right is going from. These photons are so powerful that they make air showers in the Earth's atmosphere and trigger lightning. It's just an amazing fact that they exist. And so the sun emits, and this is just a discovery from the last, I would say the last 2 months that it's been published. Right? you can actually see TeV gamma rays from the sun. So, okay, so another basic thing about astronomy that I would like to relate to you is about what's on the next slide, namely the time domain. So the time domain is a way we study the sun. We can watch it changing, right? And it used to be the only solar astronomers got to do that because the sun is close and it's changing, and we can see that happening on short time scales. But the astronomy has gotten so good that you can see the stars move and make a movie of the motion of the stars. And this is showing you an example. It's showing you our galactic center, the center of our galaxy, as a black hole, and it's marked here as a little white thing and a little white dot in the middle. So there's a black hole, very massive object that all the stars nearby swing around in orbits just like the planets around the Earth. Sorry, the planets around the sun, just like us. And the amazing thing is the spatial scale there. Each square, each image is 1 arcsecond across. And 1 arcsecond is extremely small, an extremely small angle, right? It's like, distance between Midland and Odessa, maybe the dimension of a dime seen from downtown Odessa to wherever, Austin, Texas. Okay, so time domain astronomy actually is that underpins this movie that I'll show you of solar activity, flares, and CMEs. Okay, so next slide, please. Another very remarkable, nice thing about modern astronomy is what we call multi-messenger astronomy, right? It is, you actually see an object in multiple wavelengths, different wavelengths, and so you can synthesize the physics by looking across the different bands and putting them together. And so this shows you the whole sky, or the galaxy, at least the part that is our galaxy, aligned in the coordinates of this rotating mass of stars that the sun is one of. And so from the top, radio, middle, optical, lower, gamma rays, and then at the bottom, actually neutrinos. And so this is something which just has gotten very popular in astronomy, multi-messenger astronomy. It's very exciting, but of course, we already did it on the sun, starting in 1772, when this clockmaker in London, a watchmaker, a man who was capable of doing very fine work with instrumentation, was also interested in the Earth's magnetic field, was able to see motions in the Earth's magnetic field that had a diurnal pattern. Every day they did the same thing. So I think the next slide shows you those diurnal patterns. You can see they're very clear. There's many days here, and there are 3 different stations, and each one of them has this almost sinusoidal up and down. So why would you have a diurnal variation in the magnetic field of the Earth? Right? This is a very strange concept, and it must have been 1772. It must have been eerie for them to have discovered this. And the answer, of course, is that it's day and night, right? So the sun shines on the Earth on the day side, and it doesn't on the night side. So on the day side, winds blow, the atmosphere changes, there's differential heating, and so the flow of ionized atmosphere distorts the magnetic field. So that's what's happening. And so by looking at the magnetometer in a basement room, in London, you can tell when the sun rose and when the sun set. So this is an example, the earliest example, I think, of multi-messenger astronomy. So next slide probably shows solar flares. Right, so this gets us into the nitty-gritty now of those magnetic fields that I showed looking out at the sun. And so, don't change the slide, but just remember, I'm going to go back to that cube that showed the slab of the sun with the sunlight. So this is showing you, on the left, a solar flare. The bright part is the flare, a sudden brightening that you see, especially at H alpha. That's been known for a long time, and that's an amateur's observation there. And you can see also sunspots. So these solar flares are gigantic explosions that occur near sunspots. But if you look further out, on the image on the right, you're seeing the sun in the center there, but then you're seeing the corona on a much larger scale on the outside there, and that is showing you the occurrence of a coronal mass ejection, we call CMEs. And these are the things which actually come to the Earth and cause damage to power lines, for example, and satellites. So this is something that we've learned in the last decade or two can be quite dangerous. It was quite a surprise that I was coming out of the airplane from Scotland with a Canadian who was from Ottawa. He works for the Canadian Senate, and he experienced the great power outage in 1989 when a solar flare happened in the Quebec hydro power system blew its transformers. In fact, New York was dark. It was quite a famous occasion. So it was a very expensive affair to replace these transformers and get the power grid back up. And the Canadian was really impressed by this event because the military came to his door. Soldiers came to his door and said, "You must leave your house." So, and he refused, of course. In any case, that could happen at any time. And the danger to humanity is that we've seen these things happen before, and they've been bad. In fact, they happened at the time of the first flare in 1859. The telegraph system around the world noticed this because they needed the current to flow in telegraph lines to send signals, and they could, when this event happened, like the 1989 event happened back in 1859, the telegraph operators found they didn't need their batteries. They could unplug their batteries and still send signals because the currents that were flowing, driven by this powerful disturbance that was affecting the Earth's ionosphere, was enough to cause that kind of voltage. All right, so now we're looking at an example of what's launching a CME. This is a movie showing extreme ultraviolet, taken from space, of course. It's showing these magnetic loops, right? These are coming out of the photosphere. That's the dark part here. You can see the surface of the sun. And when the flare happens, everything saturates, and then these bright loops ranging. The scale here is like 100,000 kilometers, bigger than the Earth, almost the size of the Earth-Moon system. Very large, very energetic, and you can see all kinds of things happen. It gets dark in the corona. That's the mass going away in the CME. And you can see this jiggling motion right there, which is, I think, really remarkable because this medium that we call the corona is actually a magnetic field. It is not physically anything, it's just the field. And sometimes some parts of this field have gas on them, on the field lines, and you can see them. But the structure of this thing is just the magnetic field. It's not bricks, it's not wood, timber, it is just the magnetic field. And so the jiggling there is the forces in the magnetic field causing it to vibrate. It's like a bowl of jelly. You can kick it and it won't jiggle. So I just think this is really neat. Okay, so next slide. Right, so let's go back to let's look at this. This is very complicated, so I don't want to spend too much time on it, but I will just point out that this is a series, this is a 12 time series, 12 wavelengths that are showing the development of a flare. So a solar flare happens on a time scale of a few hours, and this wavelength here, which is the lowest temperature wavelength of the corona, it's hot, right? But hotter and hottest, you get from different spectral lines, you get different views of the mass, of what's happening to the mass that's emitting. And the amazing thing is there's this dip, there's this gouge here, and we call this, technically we call it a dimming, right? So dimming happens, and that dimming is the result of the mass that's in that coronal mass ejection that I showed you coming out from the sun. The sort of thing that could come to the Earth and could cause damage and cause satellites to drop out of the sky. So that's fairly straightforward. So I think the next slide gets us into the next big discovery. What I'm doing is I'm going through a few big discoveries in astronomy and general ideas about astronomy before I get to sun sketcher itself. And I'm watching the time. I think we're okay. So this is a discovery that was made by a graduate student in Japan, Fusa Miyake. Miyake is her name. And so she's standing there in front of a tree, slab, and she was able to do analysis of carbon-14. Right? Carbon-14 is the method we use for dating organic matter, because the carbon-14 nucleus is unstable and has a half-life that's a few thousand years, and so you can date when something happened. So in the tree ring, you can take samples radially out from the core of the tree to the outermost part of the tree and see how the carbon-14 varied as a function of time. So it's like a snapshot of the movie that I showed you, but on a time scale of tens of years. But the nicest thing is that those tens of years, while the tree was growing, could have been thousands of years ago. Right? You find a fossil tree, that fossil tree will have all of this carbon-14 knowledge embedded in it. And so what she was able to do is to make a graph there at the bottom that shows the annual averages of those tree rings. And there's an event. You can see there in 775 AD, something happened. And since she made that discovery, the people have found other cases of this back to the beginning of the Holocene. The Holocene is the current era prior to the Anthropocene, I guess, but they got back 10,000 years to the last ice age. So over that time span, there have been about 8 of these events. And so the current best thinking about this is that these were super duper flare events, much bigger than we would normally get in say, a year or a decade of observations that we're getting currently from space, for example. So it's a super flare. And at the same time, the satellite was Kepler's satellite was doing photometric observations of many, many stars for the first time, just watching their brightness change on a very subtle scale. And you can see a light curve from a star there, a star that's a solar type star, much like the sun, and it has these big peaks, right? So those peaks are flares, super flares, and we know that they're super flares in the sense that they're very energetic, much more energetic than solar flares. So here's a solar type star that's making these huge flares that are like 1,000 times, 100 times to 1,000 times more powerful than the biggest solar flares. So obviously, if our normal garden variety of solar flares could do damage to satellites and burst transformers and do bad things, a flare 100 times or 1,000 times that powerful would be quite seriously affecting life on Earth, at least on the solar side, at least for some period of time. So it's a bombshell discovery, and we don't know now why these stars can do this, and we worry that if we wait long enough, the sun may do it. And so it's a topic of active research, but it's a little bit murky because we don't really have a way to predict these things. So we can follow their distribution law, but then we can anticipate them, but not very well. Okay, so that's I think the state of the art in solar physics in terms of high energy processes. Let's look at the next slide. Right. So now we come to the basic important thing here I want to talk about, that sun sketcher. So if you want to flick back to that, cut out that cartoon, I wanted to make the point that back. Way back. Okay, almost there. Forward now. One more or two more. There it is. Okay. So you see the green thing circulating there. They come back to motions. So these are. It's a cartoon view of a schematic view of what's happening inside the sun. There are things flowing like winds. The material is a gas, and so because of rotation and because of heating, there's going to be flowing, and this dynamo is there making the magnetic field, and that's distorting these flows. And so the surface there at the top is going to go up and down depending upon the nature of these flows. It's kind of analogous to the sea surface, which we can watch and try to infer it's the presence of ocean currents, right? The water piles up here or there. In the same way, that's one of the ways you can distort the surface of the sun and make it aspherical. Change it from being a beautiful disk or a beautiful circle or a beautiful sphere, change it to being lumpy. And another, of course, obvious one, even more obvious way for for that to happen is that the sun is rotating. So the rotating sun should make it oblate, just because of centrifugal force. So the oblateness is a predictable thing, almost, except that the rotation of the sun is a little bit uncertain, since we can see it on the surface. We can see the sun rotating on the surface, and it's quite a remarkable thing that the rotation that we see on the surface is a function of latitude on the sun. So the sun doesn't rotate like a solid body. It rotates what we call differentially. So the equator goes faster than the poles. Strange, but maybe typical. But then that's on the surface, and we don't really know what's inside the sun. We can do that seismologically, and that's one of the connections between the Permian Basin and relativity. This is in my first slide there. Seismology, there's such a thing as helioseismology, where you can use sound waves to study the interior of the sun, just like you can prospect for oil by using acoustic wave transmission to locate the pockets of oil in some way that I don't know too much about. Okay, so this is just illustrating that the surface of the sun can actually be interesting. Okay, so let's go back to sun sketcher slide number 1. And somebody's picture. Whose picture is that? Who took that picture? One of our Montana, or
I think Greg's wife Diana maybe shot.
okay, Greg's wife. Okay, that's an amateur picture of the diamond ring, right? So diamond ring is the last gasp of brightness as the sun is eclipsed. And you can see the clock when I took this picture was ticking 209 days before this April 2024 total eclipse. And so we're here in Odessa to practice for that with like a beta test for this app that we're using we want to use to study it. So hooray for Western Kentucky University that has done all this. And I'm just talking about it. They did it all. Okay, so next slide. And that is the diamond ring in 2017. A beautiful picture on the left showing not the diamond ring itself, but all the beads that appear as a function of time as the sun is eclipsed and then de-eclipsed. On the left and right lens, you see different beads corresponding to different structures on the moon, right? Different moon craters and valleys and mountains and stuff like that. And that picture actually shows you, I think this is H alpha, you can see red filament material there too. And on the right, that's a picture of the man himself, Bailey. Sometime before 1841, this is a picture that the Royal Astronomical Society has got in London. Okay. So the Bailey's bead is the last bright thing, and the diamond ring is the massive stuff that you see that's bright. It's the same thing. Okay, so how will our app deal with that? Basically, the secret is we're going to use the moon as an astrometric reference. Astrometric reference means that we know where the moon is exactly because people have gone out to the moon and used radar ranging and taken precise pictures, and so there's now a database of lunar structure and shape that's accurate to a few meters, right? This is an amazing thing because we don't know the Earth that well. A few meters means this room would be well resolved in this database, the structure the size of this room. So we can project that against the sun during an eclipse and use that structural knowledge from the moon to identify where this deformations of the solar surface are. So this is, in a sense, cutting-edge research because you can't do it any other way. Telescopes aren't that good, right? So the timing of these eclipses is that good, and we can do that using the app with access to this lunar database and the app's knowledge through GPS, high technology, but everybody's got it. GPS in the phone and location and precise timing, right? So this is the basis for the app. Lola is the name of the lunar reconnaissance orbiter, which made this global structure of the moon. Is making it right now, actually. Okay, so next slide. All right, this is dissecting an artist's view of what a Bailey's bead might look like. And the vertical scale there is like an arc second, so quite a small angle. And there's the Bailey's bead in the middle. just as it rotates through the eclipse and is extinguished, right? And so you can see that this angular scale there is only an arc second, and so that means the time scale is very small as the eclipse rushes through. And I think what it was, Gordon, it's 2 kilometers per second or something like that, some enormous velocity. You'll see it tomorrow as the sun rushes, as the contact point goes through Odessa. Okay, so the next slide shows what we're going to do is find the exact time of that point there, where the red line points at, and then compile that knowledge from everybody's phone and beat down the noise by having multiple phones looking at the same thing from different perspectives and at the same place at different times. And so I think it's going to be a wonderful database to the very first of its kind to be able to tell you the height of the solar surface on that day, tomorrow, I mean, just around the edge of the sun. So I think what we'll see is oblateness. We'll see it to be oblate. And we also will probably see effects of this solar magnetism that is there in the sunspots. Because this particular point in time is what we call solar maximum. There are plenty of sunspots and lots of flares. And so there is the maximum amount of this magnetic distortion that might be happening in the interior of the sun. All right, I think I just said all those things. Oh, the layout. Irene has done this wonderful thing. They're helping with this wonderful thing, many things. The one thing is to make a map. And so a map of Odessa, where the church will be, and I'll show you that in a second. But I'm thinking actually as I'm doing this that we're going to locate this Bailey's bead, 2 of them really. One of them is on the incoming side, one is the outgoing side. And so we're going to find 2 valleys on the moon, 2 specific valleys where those beads appear, right? So these will have to have names. And so I'm going to suggest that we call one of them Velas Irene, because Velas is the way that people talk about valleys. And the other we might call Velas Sunsketcher, or I'm not sure, we might have a competition for names here. But anyway, we'll find them, and we'll be able to use the topography, or the selenography from MOLA to be able to know which crater was doing what, I think. Okay, I think that's basically it, except for this map. So the little flags there where we have people. And at the very bottom is a Stonehenge, or 0.7 Stonehenge, and going up north to the county line, we should be able to cover about 30 kilometers worth of lunar topography that way. So it's not just going to be Velas, Irene, it's going to be a whole series of different points that we don't really know. We'll map out, basically we're going to map out the moon this way, and of course, we don't get a lot of coverage all the way around the sun just from this one beta test here in Odessa. It's just a single point, not much perspective. But if this works, then in 2024 we'll do it with a much broader base, and we'll be able to do a very much better job, I think. So I think that's it. Oh yeah, the relativity connection. So I'm really not an expert in this, but I'll tell you the story. The story is that in the 19th century, people were able to do astronomical observations of the planetary motions. They could do it actually very precisely. It turned out that the perihelion of Mercury, which is the point closest to the sun, that point was rotating faster than it should, because you can do the mechanics of orbital motion, and if the sun is spherical, a point mass, basically, it should have a certain precession, rotation, or rotation of this perihelion. And it was not right. They found that it was off by like arc seconds per century, some very tiny anomaly. So how do you solve that anomaly? It turned out you could solve it through general relativity. So Einstein took this fact and actually explained it. And it's quite amazing. But even more amazing is that Einstein's explanation, which is of course general relativity, and it's well established now in many ways, but it may not be right. It may not be completely right. And there are other ways to make this perihelion precession happen. One of those ways is if the sun is oblate in a significant way. And so this, our app will actually define that as better than anybody else has done before. If that is the case, then one would have to look for an alternative theory of relativity. That's my understanding of it, at least. But I'm an observer, not a theorist, not a relativist for sure. And so I'll leave it at that. But people are interested in this for that reason. So I think that's it. Thank you very much. The bullets here are, we're studying the sun for several reasons, but one of them is related to exobiology, et cetera, life on planets, that sort of thing. And the other is threats to terrestrial infrastructure through these supernova mass ejections, all related to the shape of the sun because of its knowledge about the interior flows. And we're hoping that this UTPB beta test will lead us to great success in 2024. So thank you very much.
First of all, there is still ample opportunity to sign up for one of our viewing locations. If you have an Android phone, you're welcome to participate. It's pretty automatic. You download the app, you set it up, and you watch the eclipse. And automatically the phone will turn on at the right time, send us the photographs with your permission, and you will have made a contribution, and we appreciate that. With that, any question for Dr. Hudson in the audience? Come on, be brave.
How does the 8-minute light change like affect how?
Oh, she's asking about the questions.
Is that wallet?
It takes time for the light to get from the sun to the earth, right? And the answer is that's interesting. I haven't thought about that. Have you thought about that? I don't think it matters too much because it's relative, right? We're doing a differential. And so it probably does matter, but it is at a scale that we don't have to worry about. But thanks for the question. We'll study up on that.
Can you talk just a little bit more? We talked at lunch. Can you
Yeah.
talk just a little bit more about the 11-year cycle?
Oh,
And I'm assuming that-
okay, this is what the people I had lunch with. So 11 years, yeah, so you saw the sunspots come and go, right? They wax and wane. And no, I can't talk more about it. I think that's just the way it is. And the complexity of it is not fully, I didn't fully describe the complexity of it. One of the complex things is that the sunspots themselves have each a polarity pattern, like that, cartoon that I showed you. There's a plus and a minus. So there's a leading sunspot in the sense of rotation. This first sunspot that comes by in a group is the leading sunspot. And there's a trailing sunspot that follows after that. So they have a plus and minus relationship that is different in the north than in the south. So the plus and the minus in the north corresponds to a minus and a plus in the south. That's interesting, strange, not predicted. But the stranger thing is that every 11 years that switches. So after 11 years, the sun cycle repeats again with the opposite polarities north and south. So that's a couple of parts of the complicated phenomenology, the morphology of the stuff that we see happening in the sun. There's other things too. It's a little wacko, bizarre behavior of the magnetic field. So
Talking about 11-year cycles and Earth disasters, does the Earth magnetic field do that?
Oh, is there a relationship between the 11-year cycle and the price of wheat, for example, that sort of thing?
Does the Earth's magnetic field reverse and what would happen?
Lake Victoria, the local Lake Victoria, and others, there's always been speculation like that. And
That just is not like it.
for the 11 years, you have to have 10 cycles of something before you know it's really a cycle. So 11 years is longer than my lifetime, or 10 times 11 years is longer than human lifetime. So it's a statistically tricky thing to associate any of these things with 11-year cycles. There's no obvious effects, except for the things that George, the watchmaker, discovered, the behavior of the Earth's atmosphere.
Is there any variation to how the eclipse looks on Earth just based on the altitude that you're at? Or is that like too small of a difference to really see?
Well, no, there's the radiation, if you look at the eclipse maps, right, they have the shape of the footprint of the shadow. It's never a circle. It's always an oblong, you know, it's really weird the way it varies. And so that's because the radiation is coming in slosh-wise. And so that's a factor in this timing. We're doing this very precise timing that we have to worry about flight travel time. There's refraction in the Earth's atmosphere, which has a small component of time delay in it. So that's something else that we'll have to worry about if our data are as good as we think they are. Well, okay. And that's one of the reasons the smartphones are not perfect devices, because they have very uncertain color response. The refraction is a very color dependent kind of thing. But it's a good question.
Yes, sir. So, if I'm right, one of the obvious signs of a solar flare or high activity of the sun is the northern lights, right?
Activity of sun, northern lights, flares.
Oh, aurora. Yes. The question is, how does that work? You're asking how that works?
If there's a direct relationship, right?
Not a direct relationship. It's a close relationship, but it's complicated. And that's it's a story that I love because it's the Norwegians, Bip Birkeland and a couple of Norwegian astronomers, pioneered this kind of study. And it learns very important things about plasma physics just from the behavior of the northern lights. Plasma physics, as you all know, but you perhaps don't know, is plasma is the fourth state of matter: solid, liquid, gas, and then gas that is ionized and fully ionized. It can be fully ionized. So the auroral emissions come from ionized gas, which is due to the presence of energetic particles, fast electrons or protons that are accelerated by magnetic fields in the Earth's magnetosphere in a complicated way, owing to, if I got my story straight, distortions of the Earth's magnetic field due to the impact of this coronal mass ejection. So there's a chain of response, but it's complicated, very complicated, not direct. What Birkeland thought was that it was actually quite direct. And in fact, some kinds of aurora are fairly direct because the magnetic field of the Earth is sort of like a dipole, but at the north and south poles, the field doesn't close into these Van Allen belt structures, but opens out into the solar wind. And so there is a path for particles to get directly from the sun to at least Fort Churchill or Stockholm or someplace north or south. Yes?
Yes, sir.
If SunSketcher works out well tomorrow, are y'all planning on doing an iPhone app as well?
I missed one part.
If SunSketcher works out well tomorrow, are y'all planning to develop an iPhone app?
Yes.
In addition?
Yes.
Which one of you people is
So I have an iPhone gun myself, and so I love it. But the iPhone apps are harder, right?
Yeah, it's currently in development.
In development. But there's time. There's plenty of time. She can do it. So I'm hoping.
I'm going to comment on that briefly. We started doing Android because it was more straightforward. Since this is funded by NASA, there's been a little bit of pressure on us. Like apparently all the folks in NASA headquarters own iPhones. So they want to make sure they can do it too. But yeah, that is under development. A quick question for the group. How many people is this your first solar eclipse? Okay, second. Third.
So you like eclipses, don't you?
Fourth. Okay, how many annular eclipses? One? I would one. Okay. And the big one, total eclipses. How many people have traveled more than, say, 500 miles to see an eclipse? How many people have traveled more than 4,000 miles to see an eclipse? How many people are going to go watch the next eclipse on April 8th? Thank you. Be there or be square.
The next pretty good total is maybe in Patagonia. So if you like to travel, think Patagonia of the Romans.
Well, we really hope you enjoy the experience tomorrow, as well as the scientific value. I want to stress, having done a few eclipses myself, it's very tough to concentrate on the science when you're just got all this stuff happening around you. Things to look for. That shadow comes down Route 385 there at 1,000 miles an hour, which is faster than I can drive. and if you're watching it, take a look at the sun. You're missing a lot. Get a colander, you know, a spaghetti strainer or something, right? Because that's lots of little pinhole cameras. And let the sun shine through it and look at all the images. And this will be almost unique because of annular. They will start off as circles. You won't even know they're circles. Then they'll turn into kind of fat crescents like croissant. Then it'll turn into little skinny crescents. And then it will turn into overlapping circular rings, like the Olympic rings. Take a photograph of what's happening. If you don't have a colander, go stand under a tree. Right? And you see the waves doing this. And take a little bit of
We're in West Texas, country.
You have to squat down.
Bush.
watch what the animals do. Watch what other humans do. Right?
Yeah, we're gonna.
You got about a couple of minutes in the middle there to just please enjoy the experience. We traveled 18.5-hour drive yesterday. Yeah. One for the Abbott, two, I think a lot of us enthusiasts just wanted to watch those.
So the story about the mega movie, the 2017 app, we thought seriously about letting the smartphone record sounds, because then you would have this wave of, oh! But often, the words that people use are kind of vile. They say, I won't say what they say, but you hear a lot of that stuff. It's just a wave of darkness crashes through and they see the corona for the first time. It's really awe-inspiring.
And that's the key. If you can't find a tree, and you can't find a spaghetti train, just take your fingers and make a cross like that.
Like a pinhole camera.
And look at the shape. You'd be surprised. You do that, it makes a circle on the sidewalk. You do that tomorrow, it's going to make a little crescent. And then it'll make a ring. Then it'll make a crescent again. And you can try making holes of different sizes. Yeah. And think of your own little thing, too. Let us know what they are. You know, over the boat. Tell Irene, and she'll let us know what your favorite part of tomorrow was. That'll help us, get more folks to participate next time as well. But really enjoy the experience. Weather's supposed to be beautiful. Weather forecast is more like 60 degrees. That doesn't count the fact that someone's going to turn the heater off starting at 10 o'clock. It's going to be even colder than that, so wear a jacket. Henry has a UTPV brand new sweatshirt to wear. And he's going to go buy one. Greg's going to go buy one because
Son gets in the car.
it's going to be cold tomorrow. It's going to be great. Sorry.
It's Friday the 13th, I'm good.
It is Friday.
It is Friday the 13th, at about 5:50, we experienced a problem with the app. So, we've got it fixed. Yeah. But some of you, I will need to just go ahead and open the app up, close the app, and reopen it. It should show a user ID at the top. If that user ID says -1, come see me out. We have it fixed. Just do that real quick, we should be good. But if it still does the -1, just come see us.
Let me inject that. One of the challenging things about doing this is dealing with the fact that we live in a world where cybersecurity is very much an issue. So our folks at WKU that run our servers suddenly noticed a lot of people requesting information from it, panic, they shut it down. So we now apparently reopened it, but that means, as Greg said, if you already uploaded it, or if you don't know whatever one it is, we thank you. Do it again.
If you don't, you shouldn't have to reinstall it, just close the app, reopen it, and it should show a client ID at the top, it should show a number. If it says -1, just come see us out.
And that ID number is on the survey form, so it's so that our server knows which phone it's requesting data from. It's the purpose of that number. We don't know who you are.
Brilliant, brilliant.
We don't care. But we do need to know where that phone was and what time it was taken, so we need each individual, and we'll ping them all sequentially, which is why they have the ID number, which is why we respectfully ask that you close it, reopen it, get a new ID number. Friday 13th. Yeah.
you, Doctor.
Real quick, I just wanted to make some closing remarks, just get everybody prepared for tomorrow. My name is Brian Shedd. I'm the Executive Director for the Office of Innovation and Commercialization at UTPB. I work here in the CEED building. I wanted to just point out Irene back there. We've heard her name mentioned a few times, so Irene, thank you so much for three research teams from across the country that are traveling here to UTPB to conduct research for this event. So just to go over the schedule for tomorrow, we are going to be setting up at 9:30 on the main campus in Odessa, so not here, but the main campus. So 9:30 we'll be there. The eclipse starts at 10:18 a.m. It is the full eclipse at 11:46, and then the end of the partial is at 1:21. So we'll be out there the whole time. We'll be on the Mesa deck, so kind of the back side of the Mesa building, and also in the quad there. We'll have plenty of classes to hand out, so bring everybody with you. And then starting at 2 o'clock, we're going to have STEAM Fest, which is a whole bunch of science demonstrations. Should be a lot of fun. Really targeting more kind of 3rd grade to 12th grade, but if you're a kid at heart, you'll enjoy it too. We have a whole bunch of demonstrations going on, live screen printing of t-shirts, ceramic firing, glass blowing, a whole bunch of science demonstrations. And actually the cell phone stands, if you picked up a cell phone stand for the SunSketcher app, those were made in our makerspace at the library, which is right off the quad. Yeah, these. So John was working hard getting all these printed. We're going to have the makerspace open tomorrow afternoon. So if you want to come out and 3D print something, 2 to 5, right after the eclipse, you can hang around the campus and we'll have a whole bunch of fun stuff going on there too. So, get the demonstration there, yeah. All right, but thank you all for coming. I wanted to say thanks to Jackie too for organizing the event tonight. So thank you, Jackie. Great job.
I would like to just make one more announcement if we could. I'm sorry, but Travis wasn't able to assist in the presentation. Travis is our app developer. He's the one that's been out here in the hallway fixing this problem. No idea. Travis.